Hi, today's talk will be by Avinash talking on risk-sensitive, security-constrained economic dispatch via critical region exploration.
All right, yeah, I'm not going to repeat the title because it's kind of a handful, but this is some joint work done by me, Professor Bose, Ye Guo, and Lang Tong. To begin, let's consider the standard economic dispatch problem, which seeks to minimize some dispatch costs subject to engineering constraints, such as Kirchhoff's laws and capacity limits. System operators frequently solve these types of problems in real-time markets and for day-ahead markets. They also must ensure that the system remains stable given potential outages or failures, also called contingencies. If they don't, this can lead to blackouts, which can affect a large number of people. So in the following talk, I'm going to split it up into two parts. The first, I'm going to be discussing our proposed risk-sensitive formulation, which I will construct and motivate using existing formulations in the literature. In the second part of my talk, I will demonstrate that this RSCED formulation is difficult to solve at scale, and I will propose a decomposition approach to solving this problem. So I guess to begin, let's look at the standard economic dispatch problem formulated mathematically. Given some generation at each bus, denoted by G, we have some linear cost assumed to be C transpose G, and we are subject to capacity limits on generation, and the net power injection at each bus must be within some feasible set given by Kirchhoff's laws and line limits. In this case, we haven't incorporated any contingencies or outages, so to address that, we propose a preventive security constraint economic dispatch, or PSCED. Here we can see it's the same as the formulation in economic dispatch with an additional set of constraints to ensure that the net power injection at each bus remains feasible given any single line failure. So this formulation, it's secure, but it's also conservative. So line flow limits are thermal, so you can relax them temporarily as long as they don't exceed their thermal capacity. And generators are able to ramp to compensate for changes in the grid topology. So to address this, let's take a moment to consider how to relax line flow limits. So let's suppose we have some contingency that occurs at some point in time. Immediately following this contingency, we allow the line to exceed its capacity to the drastic action level, which we can maintain for up to 5 minutes before reducing it to the long-term emergency level, or short-term emergency, sorry. That we can maintain for an additional 10 minutes before reducing it to the next level, and in this way we bring the line back to its nominal level without exceeding its thermal capacity. So using this and generator ramping, we can then propose a corrective security constraint economic dispatch where we model this recourse action of generator ramping. Here we augmented the constraint for the PSCED case with drastic action line limits, and we now consider a time period in the future where we allow generators to ramp modeled through delta G. This must be within generation capacity limits, and it must be within ramping limits, and the net power injection is within the same set of constraints as the preventive case, but we now adopt the short-term emergency limit. So there are a couple of problems with this formulation. In particular, if there is no feasible solution, we can't solve this problem, and this is due to the fact that we are absolutely ensuring that all load is met. So if we allow some load to be shed, we can perhaps ensure that this is feasible, but at the same time, there is this trade-off between cost and reliability of meeting load. So in order to address this, we propose a risk-sensitive security constraint economic dispatch formulation, or RSCED, where we provide a trade-off parameter between cost and reliability. We will then show that this is difficult to solve and provide a critical region exploration algorithm, which uses decomposition to solve this, and can also be used for the CSCED formulation as well. So to begin, this is our proposed RSCED formulation. Here we allow for potential load shed modeled through delta D, which we ensure is within the short-term emergency limit for the net power injection. Additionally, we no longer take the cost to just be C transpose G. We take it to be the cost of the nominal generation plus a random variable, taking values of the cost associated with each contingency occurring with the probability of that contingency. So this is now a random variable depending on the realized contingency. So we could minimize this in expectation, like minimize the average cost across all potential contingencies. We could minimize the worst case, like the most expensive contingency. But in this case, we've chosen to minimize the CVAR, or conditional value at risk, which generalizes both of these forms. Before I continue to explain what conditional value at risk is, here is our proposed recourse cost structure, where we have some cost on regulation up and down, and some cost on load shed modeled through the value of lost load. From here, let's take a moment to explain conditional value at risk. Well, that's weird. All right, so there is some distribution on there, but you can't see it right now. So if we fix the decision variables like delta G, delta D, G, then we have some distribution on the cost, which should be shown here, but is not. Yes, it's a hidden risk. So with this distribution, the conditional value at risk measures the average cost of bad costs, or more expensive scenarios. So in this case, we take alpha to be 0.95. So we consider the 5% of most expensive cases, and we take the average cost in those cases. There is some distribution that goes like that. So this is the most expensive side. So then minimizing CVAR amounts to trying to determine the decision variables that would result in the lowest average of bad costs. Right? So given a decision variable, you have some distribution for which you can compute CVAR. Minimizing this is trying to determine which distribution minimizes CVAR, and the distribution is a function of your decision variables. So that's effectively what we're trying to do. As we can see, if we take alpha to 0, we consider the entire distribution. So we're now minimizing expectation. And if we take alpha to 1, we only consider the most expensive case, which is minimizing the maximum cost. So there's kind of two reasons that we chose CVAR. One is the nice mathematical properties. It's convex, and it admits this nice formulation here, given by Rockefeller and Uryusov, which we can use for decomposition. And the second reason is this parameter alpha gives us this trade-off between cost and reliability, which I will demonstrate shortly with this simple 2-bus example. So we consider this 2-bus example, some generation, some demand at each bus. We have one bus that has cheap generation, the other has more expensive generation. Solving this with the nominal economic dispatch, we get a cost of $20 per hour. In the preventive case, the additional constraints make the cost go up to ensure that there is no load shed later on, and we incur a cost of $25 per hour. In the corrective case, we've chosen to augment the problem, so now we've included load shedding, and we're minimizing the expected cost. So this is like minimizing the expected value of our RSCHED formulation. As we can see, this is equivalent to solving RSCHED for low alpha, which is what we would expect. And as we increase alpha to 0.9, we incur a higher cost, which is the result of decreased load shed. So this gives us this trade-off parameter, alpha, which is great. Now, this is a nice, simple 2-bus example, but we really care about practical power networks, right? So even assuming a linearized power flow model, you would think it's just throw it at a regular solver, right? However, that's not generally the case. As we can see in the 2383 bus Polish network, while the economic dispatch has a very tractable number of variables and constraints, the CSCHED and RSCHED have an explosion in the number of variables and constraints, and they're not solvable by traditional LP methods in the times required for dispatches in real-time markets as well as day-ahead markets. So this begs the question, how do we solve this problem? Right? I mean, it's huge. And the obvious solution to us was decomposition. So RSCHED and CSCHED, assuming a linearized power flow model, can be expressed in the following form. We have some cost on x0 plus the sum of some cost on xk for each k. And we have constraints on x0 and an additional set of coupling constraints between x0 and xk for each k. Now, this can equivalently be expressed in the following form, where we now decouple x0 from xk. And the cost associated with xk in the original problem, which is referred to as the master problem, is now the solution to this optimization problem, or we will refer to as subproblems. Now, our algorithm takes advantage of some of the properties of this subproblem. In particular, it's piecewise affine, convex in x0, and is a multi-parametric linear program linearly parametrized on x0. It's a lot of mathematical jargon, and I'm going to try and take a moment to explain what it really means and what we can gather from this. So because it is a multi-parametric linear program linearly parametrized on x0, the solution jk star describes a polyhedral partition of x0 over which the cost is affine, piecewise affine. That's a lot of math, but graphically it's actually very simple. So let's suppose x0 lies within some set given here. Because it is a polyhedral partition, we can separate this set x0 into polyhedral sets. That's standard like quadrilaterals or polyhedrals, stuff like that, right? So this is a polyhedral set, and the cost over each of these sets, the cost jk star, is affine, which is nice. So now we have, by plugging this into our master problem, we now have a linear program, a linear cost on x0 with linear constraints. But it's a much smaller problem than the original problem that we had. It's only the dimensionality of this problem will only be in x0. Right. So now let's suppose we had a second contingency. This would introduce a new set of critical regions. By taking the intersection of these critical regions or polyhedral sets, we now have a new set of critical regions over which the cost is affine in each region. Right? So then we could solve the master problem over each of these critical regions, and it's a much more tractable problem. We could determine the entire solution space, figure out the answer. However, in the next few slides, I'm going to show we have a systematic approach for solving this problem. There we go. So let's suppose we start with some x0 given here. We then determine the critical region in which it lies, determine its properties and associated cost, and then solve the master problem shown here over this region, which we can guarantee will go to a vertex. From here, we try and verify if this is the optimal solution, given the information we know about the critical regions we've explored. From here, we aren't able to determine whether or not this is the optimal solution, so we then perturb the solution into an unexplored neighboring critical region, determine its properties, and optimize over that region again. With this increased information, we now know about two neighboring critical regions. So we can, again, check for optimality. In this case, we are unable to verify it. So we once again perturb it into a neighboring unexplored critical region and do this process all over again. In this case, it goes to a new point. Here, there are no unexplored neighboring critical regions, so we can guarantee that this is the optimal solution. This is not the only case, but it is a very simple case of showing that this is an optimal solution. Now, I've assumed that we can both check for optimality and perturb into an unexplored neighboring critical region without going back to something we've seen before. But I won't go into the details of how that works. If you want to see, here's the algorithm. It's a lot of math. But the important thing is that this algorithm admits finite time convergence, which means we will never cycle or never get stuck, and we will always get to the optimal solution eventually. So now that we've seen the algorithm, the real question is, can we make it work? And to do that, we consider the IEEE 30-bus network with the following augmentations. I implement the algorithm in C++ and assume that slack variables are added to the subproblems to make sure that it's feasible. And the initial point is taken to be the solution of the master problem, where we've augmented it with the drastic action limits from the pskid case. Now, solving this, we can see, generally speaking, for high value of lost load, as we increase risk aversion, the system operator is less likely to shed load, and they're more willing to incur higher cost of nominal generation. Additionally, the RSCHED formulation is trying to balance between cost of all recourse action, which we assume to be load shed, as well as the cost associated with regulation up and down. So when the value of lost load is low, close to the value of regulation up and down, there's a balance between the two that it's unable to really handle in the way that we would expect. As we can see, when it's low, there is some increase in load shed despite an increase in risk aversion, which is interesting. Generally speaking, value of lost load is much, much higher. So we would see things more to the right, which is what we'd expect. The last thing I'd like to point out is the runtime of critical region exploration, which the more regions we have to explore, the more time it will take. So the farther the initial solution is from the final, the more critical regions need to be explored, the longer the time will take. In this case, for low risk aversion, the solution was very close, and as we got farther away, it took more time, which is what we'd expect. So that's basically the algorithm that we've seen. And what we showed today is a risk-sensitive, security-constrained economic dispatch formulation, where we give out this parameter between cost and reliability. And we provided a decomposition approach called critical region exploration, for which we solve this. In the future, we want to compare this to existing techniques such as Bender's decomposition, accelerated ADMM, and other algorithms like that. We also want to implement this for larger systems like practical networks like the Polish network. And we also want to augment it with variability in wind generation. Yeah. Questions? You still have access to the dual variables, so you could.
But dual variables of not minimizing cost, right? But this still makes sense.
That's a debate I don't know the answer to. I'm on both. I understand both sides, and I don't know. I don't have an answer for that. Because I think somebody should be paying the cost. It doesn't make sense to me that your cost is not justified by your dual variable. But
It is a deep question.
yeah. All right.
Next talk will be by T-Pine on feasibility study and optimal design of air core fully superconducting machine for 10 megawatt offshore wind turbine. Thank you.
Hi, my name is Thana Deepan, and you can call me Deepan. So this is a NSF-funded project, and I'm working with Dr. Haran and postdoc Dr. Lee. So this is where we are trying to see the feasibility of a fully superconducting machine for an offshore wind turbine. So as you can see that why we are looking for an offshore wind turbine is clearly shown in the picture. As you can see that when you go from copper wound to the gearbox machine to like permanent magnet and partially superconducting and to a fully superconducting machine, and the weight and the size reduction is very huge. You can see that. So, like this. Oh, this one. Okay, so this is the copper bound gearbox, and then from here to permanent magnet, and then partially superconducting and fully superconducting. As you can see that if you go for a fully superconducting machine, then it will go less than 150 tons. It's a huge weight reduction if you look at this. So the NRL study found out that if you go, and other than the weight and size reduction, there are other additional benefits of going to a fully superconducting machine. For example, we can increase the capacity from 10 megawatt to 20 megawatt machines can be built. And also the efficiency also increased because when you use superconducting winding, then you can reduce the resistive losses, and also so that's also one of the way to increase the efficiency of the machine. And also you can see that as it is pointed out that we can reach weight reduction from 30 to 50%. And also the next benefit is that the permanent magnet cost high because they use rare earth magnet. But if you go for this kind of machine design, we can use like, for example, MGB to use normal material, so you can go to 10 to 20% reduction in the cost. And also because it has a very large capacity, we can increase the efficiency of the partial energy capturing at partial load. So altogether will contribute to the reduced levelized cost of energy if we go for a partial superconducting wind turbine. Here I put it in a chart that what are the options we have. We can have a partial superconducting machine. This one is is very well explored, and there are a lot of machines built and demonstrated. And here then we have a fully superconducting machine. So this one is further improve the efficiency and also reduce the weight, but it's not very well explored because we have numerous challenges to build this machine. One of the challenges, if you go to a fully superconducting machine, the cost will increase because we use more superconductors. And also one of the other challenges that AC loss. Because the fully superconducting machine, we use the superconducting material not only in the field winding, but also we will use in armature winding. The armature winding the superconductors will experience varying magnetic field and also alternating current, which will contribute to AC loss. And also when you have a superconducting machine in rotor and the stator, then you need to cool this winding. This create problem of cryocooler design. And also we need to transfer the torque. So those also one of the other problem, and how we are going to integrate this machine in the actual wind turbine. So there are a lot of several companies working on this one, like GE and Siemens, AMSC, American Superconductors, and AML. And this is one of the GE built partial superconducting wind turbine. They already built and demonstrated. There are other machines also built and demonstrated for marine propeller. So, but these are all a high temperature partial superconducting machine. None of these built for a fully superconducting machine, which that's why we are focusing on these fully superconducting machines. Okay. So what I did first is I just went through a literature and try to identify what are the machine design already available in the literature. What I found out that so most of these proposed machine in the megawatt range from 10 to 15, and the efficiency is around like 98 to 100%, 99% efficiency, and the diameter is varying, and from 5 meter to 3.67 meters, and then we have a different design, like we can use the iron core in state as well as rotor, or some people design there's no iron core, but they have the sealed iron. But there are another design that there's no iron core at all. Because why we talk about the iron core? Because these machines are built to have like 10 Tesla, 4 Tesla, so this will saturate the iron and then core loss will increase. And also when you increase the field strength, and the AC loss also will increase. So after we went through all of these design, we found out that this is removing the core completely from the machine using a seal coil will reduce the weight of the machine, and also will reduce the core losses. So it is more feasible design for a offshore wind turbine. So we want to explore that particular machine for this project. So this is an abstract design, which not show all the full mechanical design, but it's the one in the left show sealed coil design, and the one on the right show the iron core design. Iron core design means we'll have a very heavy the iron shield in the outside the machine, and also we'll have the iron core inside to increase the flux density, to have very well the flux density. But the problem is that it will increase the weight. They increase the weight of the machine. So here, what we did in our machine is that we remove the iron core and we replace with the seal coil. What will it do is it will create an opposite magnetic field to contain the magnetic flux within the machine. So what is the advantage of doing that? We can so using the active seal, we are eliminating the magnetic flux outside the machine, and also there's no core loss. And so we can increase, and also we don't have any problem with saturating the iron, so we can explore high magnetic field, and also we can reduce the weight further. And also we found out that the preliminary calculation that the estimated AC loss in the windings are less with this design. So one of the to do that, we need to go through all of these design. First, we need to look at the winding design. So we for this one we pick up MGB2 windings. So this this one is cheap in the current market compared with other high temperature superconductors. And this is one of the coil built and tested in UIUC by previous senior student. So this one is actually built for NB3SN coil, but we are in this project we are trying to explore for MGB2 winding. So this is the proposed the arrangement of the sealed coil and field coils. So, and also we were looking at the mechanical design, how we are going to design this machine. There are two kind of options available. Since it's a fully superconducting machine, the superconductors will be in the rotating rotor and then also the armature. So we can have a separate cryostat for the rotor and the stator, or we can have a one cryostat containing the whole coil. It has the associate problem because if you have something like that, but still you need to the efficiency is less here, but here the efficiency can increase because and also its maintenance easy because you have a separate cryostat for the stator and the rotor. And also we were looking at how we are going to integrate this machine into the actual wind turbine. There are two options available, but the conventional integration, and there's another option proposed in the literature that mounting the generator in front of the blades. So the third problem is the cryocular design. So for example, I plotted against a temperature to the input power for a 1.5 watt. You can see that these are the available cryocoolers in the market. For example, for a 1.5 watt at temperature around 20 Kelvin, if you want to extract 1.5 watt AC loss, then you have to apply around 90 watt. For example, this one, if you are operating at 4 Kelvin, then if you to extract 1.5 watt AC loss, then you have to apply around 2 kilowatt. So see that, for example, if I am using NB3Ti winding, so low temperature superconductors, if I have 1.5 kilowatt AC loss at 4 Kelvin to extract that, I need to supply 2 megawatt power to the cryocooler. So then it will reduce the efficiency. But so for example, that's why we choose MGB2 winding, because these can be operated at 20 Kelvin. So at 20 Kelvin, if I want to extract 1.5 kilowatt, then I need to only supply 90 kilowatt cryocooler power. So then we can achieve around 99% efficiency. Here we can only achieve 80% efficiency because most of the power will go into the cooling the windings. And also this figure show the weight comparison of the available cryocoolers, and you can see that when we go for a low temperature cooling, then the weight will go very high. So here now we are looking around 20 Kelvin. It is around 10 kilogram. So for example, 1.5 kilowatt, I will end up having 10 tons will be dedicated for the cryocoolers. So with this all, So with all these things that we did is we first designed a base model that we explored that with the seal coil. We designed our machine and tried to understand that how these the EM design will look like. So these parameters we choose because normally the outer diameter we choose as 2 meter, because that is the this is coming from the restriction to move these machines from factory to wherever we are going to install these machines. From the 2 meter, we figured out all the other radius of where we are going to place this is the armature coil, this is the field winding, and this is the seal winding. With that, we did some EM design. This one showed that this picture showed that without the active seal, so you can see that how the flux line look like, and then we activated the seal coil, and then how it contained the flux within the machine. So once we activated the seal coil, we look at the field density at the air gap. There's not much difference, but of course it went a little bit less than the without the seal coil. So seal coil reduced the flux density in the air gap, but a little bit we can compensate that. But the advantage of having a seal coil is it will eliminate the field outside the machine. And also we look at that how the seal coil affect the the position of the seal coil affect the flux density outside the machine. So we looked at that moving the seal coil a little bit outward toward the end, and also we looked at that we move the seal coil will close in the radial direction, how that is affecting. And then we figured it out when we the optimal position of the seal coil is when we place the close to the when we increase the radius and also close to this position. That's where we see that we can minimize the seal outside the machine. I don't know why this is not working. Oh, sorry. Okay, after that, one of the critical challenge of the fully conducting machines, the AC loss. What is AC loss? Because in the if we use the superconductors in the fully superconducting machine, we are going to use the superconductors in the armature. So these will experience the alternating current and also the alternating magnetic field. This will contribute to losses in the superconductors. For example, we can model this one using a critical state model. So what it is for example, here I show three states. For example, here the positive current is going through. What will happen is in the superconductors, when the current is what will happen is that the current will only take a certain region to go through. And here when we have the positive and negative current, you can see the gray is so the negative current region and this one was the positive current region. So what will happen is that when you change the current, this region will change. So whenever the regions first conduct the positive current, they will conduct a negative current, then again negative current regions again conduct the positive current. This change will generate the losses in the conductor. The same things will, when we change the magnetic flux, what will happen is that when the magnetic flux is applied to superconductors, they will generate a screening current that will prevent magnetic flux penetrating the superconductors. So what will happen is that when you increase the flux density, the screening current increase. So after one point, what will happen is that if you increase the flux to a certain level, then what will happen is that they will not generate more screening current. Then the flux will start to penetrate the superconductors, and then the superconductors will lose their superconducting property. So, but when you change the flux density, what will happen is that the screening current will also increase and decrease. This will contribute to AC loss in the superconductors. So we need to evaluate these AC losses in the machine because the armature will experience in the both effect. So for this one, that is only for a circular superconductors. But in our design, we use a multi-filament wires. Here, each of the region is superconductors, but it is embedded in a copper matrix. So for this one, Wilson showed that the AC loss can be calculated using these equations. So this one is actually the experimental results show that how we can calculate each of these function. So we use this model to evaluate this AC losses in the superconductors. So to evaluate the AC losses, what we did is this is our armature winding. So we evaluate the flux density in the four regions, and we calculate the AC losses in each region. So this graph shows that how the flux density changes in the armature for each region. So the better calculation will be calculating for each point, but it is difficult to calculate for each point. What we did is we approximated that we divided the armature into four regions, and we assumed that each region have the same flux density. And the calculation showed that the AC loss in the armature is 650 watt. So this is so if we want to remove this AC loss, then we need a 65 kilowatt cryo power, and then if you include all the other heat, radiation, and conduction loss, we will still be able to reach 98 to 99% efficiency in the machine. So this I have the final result of the machine. So we with all these calculation, we also evaluated what is the length of the superconductor we used in the machine. So the total we used 223 kilometer. So if then I compared with this superconductor usage in the other machines proportional to literature, it's still in the same range. But there are some other machines that use less than this one, but they use iron core to reduce the superconductor, but this is a fully superconductor. So our idea is to reduce the weight. So in that case, this is a reasonable length of superconductors. And then after that, because the first design we picked these numbers, we fixed these numbers. So we wanted to evaluate that whether changing all these parameters can we further reduce the weight of the machine, and also whether we can reduce the superconductor usage of the machine. So what we did is we made all this as a variable. So we are trying to see what is the best design that result in reducing the weight of the machine as well as the usage of the superconductor. So this is our objective function we choose, where A1 and A2 are the tuning parameters, and we are trying to minimize the superconductor volume and also the shield ion volume. So here what we did is, rather than replacing the shield ion fully, but we introduced the shield ion again. So we are trying to see the combined effect of the shield coil and the shield ion. So for example, if I set A2 to a larger number, what will happen is that we are going to see a design that will minimize the superconductor volume, minimize the shield ion volume. If we set the A1 to a larger value, then we are going to see a design that minimizes the superconductor volume. So what we did is to find the designs, what we did is we fixed the pole number. We also consider we also try to see which pole design will give you a minimum weight and superconductor usage. So we fixed the pole number and fixed A1 and A2, and we changed the values between we fixed these ranges, and we changed all the values between them to find what is the best what is the best design that we can obtain. So here I have the flow chart of the optimal algorithm. How we are going to do is, we are going to first choose this, using genetic algorithm, we will choose these values, and then we will feed these values into the flux model, and then we design this model in the flux software, and then we get the torque profile and also the flux density, and we using all these values, we will calculate the AC loss and leakage flux. We will calculate, and we will compare with our limit, and if this limit is exceeded, then we will discard the design. Otherwise, we keep the design, and then we will move towards the more optimal design space. So for example, this is still we are doing that, but this is our expected outcome that we are trying to, this is what we are trying to reach, where we will have the total superconductor usage and weight, and we will have all this design where we will try to figure out which design will give us the weight. So we can choose whatever the design we want. For example, if we want to reduce the total superconductor usage, then we will go for a less weight but superconductor uses higher design, or we can go for a low superconductor usage where we can increase the weight. For example, this one show that the more this design show more shield ion placed, but this show there's no shield ion. For example, with this one we did some preliminary result. This shows that, for example, here you can see that I compare two different design we obtained from our optimal algorithm. Here you can see that we have more shield, field coil is very large and the armature coil is very small. and here we have different design. But with these two design comparison, we were able to reduce the total superconductor usage by a 40%, and also we were able to reach less than 1 kilowatt AC loss. So, but we haven't finished this optimization, but in the future we will be able to obtain a very good design whether we can reduce the superconductor usage and the weight. Thank you very much. This is part of my qual presentation, so you can give a feedback and ask questions.
What are Maxwell's equations? How did you choose your current density on all those three windings?
The current density of these windings are decided by superconductor current density is decided by the applied field strength and also the operating temperature. So, for example, we are operating at 20 Kelvin, and our air gap flux density is 2 Tesla. We tested 2 Tesla, and using those two, we choose the current density.
So in your optimization, when you're optimizing, you are changing the
You
are changing the value of the shade, or
yeah, we need to change. How we are going to do is we are going to, once we get the flux density, then we need to feed the flux density into the design, and then we need to get the flux density. So we need to go backward and forward. So for example, for the first in the first design, so we fixed for example in the first base model, we fixed every value, all the values. We said only so for example here I have the, so in that one we don't change the current density, but in the second optimal design we are going to change the current density according to the air gap flux density. We will change it.
Can you go to the slide where you're showing your Pareto set for your optimal solution?
Which one?
The top one. The dot one. Your Pareto set.
Oh, that's not the actual result, but I don't know why it is not working. Again, this. This one?
Yeah, that one right there.
Yeah.
So the design that you're highlighting right there, design number 39.
Yeah.
Why are you highlighting that design?
No,
And
it's
what's causing the spaces in your Pareto set.
Yeah, this one is just an example. I put it here, but it's not the actual design I am targeting. But for an example, I saw it here. Like, so when we plot this one, how the output will look like. It's not the actual design we are looking at. We haven't finished this optimization.
Okay.
But we can pick any design that I mean. The idea of we have this A1 and A2, so we can pick any design we want. For example, if somebody wanted a design which less superconductor usage but reduce the cost, then we will go for a design that using the maximum reduce the superconductor usage, but we will increase the shield ion. So we can choose which design according to the application.
So there's a trade-off between the weight and the superconducting.
Yeah,
That's
yeah.
So I want to get really the utopia point is I want to have super high superconducting and as small of a weight as possible.
Yeah.
But that's impossible to do, right?
Yeah. That it will increase the cost because superconductors will increase the cost, while the shield ion will reduce the cost. So we are trying to see, for example, if I fix A1 and A2 to 1 and 1, then we can see kind of balanced design where we can reduce the cost and weight to balance.
So is your actual Pareto set, is that 3-dimensional rather than 2-dimensional that you're showing? Because you have a cost term in there as well?
I mean, 2 dimension. We only have the cost and weight. So that's what we are trading. Yeah, cost and the weight.
Okay.
So in the cost, in the term that we talk about is superconductor volume, and then we talk about the weight. We just consider the weight.
Just a quick question about I don't know if you commented on it, but if you haven't, can you comment on your reasoning fixing the pole count?
We are not fixing the pole count here. So we are at the moment. So for example, in the base model, we only picked one of the when I saw the in this base model. Oh, sorry, I gone all the way up. So for example, we are considering all these poles. So we will get an optimal design for each number of poles. We are not fixing the poles. But for the base model, we considered 40 to try to see how it's look like. But in the next, in the optimal design, we are going to get an optimal design for each number of poles. So and then we will see which one is best for this application.
So the end goal is to apply this to offshore wind,
Yeah, offshore wind.
and then you're saying that you want to look at the levelized cost of energy.
Yeah.
Did you think about trying to minimize that as your optimization problem?
No, no, not at this point. But so, for example, at this moment, we were trying to figure out most of the design problem, like how to mitigate the AC loss and how to design the cryocooler. And the plan is to come up with the complete design. For example, when I look at the literature and what I identified is that, for example, all of these design did not solve all the problems. So somebody calculate the AC loss, but they don't estimate how much superconductor they used, and so there's no complete design so far. So we will try to see whether we can address all the problem, and none of these design they don't have the actual mechanical design that how the torque can be transferred. For example, we have the cryocoolers, and we need to connect the cold parts to the warm parts, so there are problems. So we will try to see whether we can solve, and then we will go there and then to see. Yeah, that one is the sealed coil design is proposed by Dr. Haran, and some initial studies done, but that's also not fully done. So those they have done research on whether they can apply this machine for a aircraft application, but none of them looked for a wind turbine. So we are focusing on wind turbine.
Wait, how can Professor Heron's machine have a same output if the actual length is like?
Yeah, very small.
Yeah,
but they are, for example, the air gap is very small on their design. For example, this one is 130, 100, 185, 100 is one air gap. That one only have 40 millimeter. Yeah, 46 pole, and also it has 3 Tesla. So for example, this one is, for example, you need to have a higher air gap because you need to accommodate the cryostats walls, and also you need to accommodate some shield to separate reduce the flux, the alternating flux. So those are really problem. So that's why they have like 100 millimeter air gap for this machine, because the flux density very high. So you can have that. So I mean, there are a lot of need to be considered. So that's.
So where does your machine lie compared to all those?
I mean, our machine is the same machine, but we are trying to explore more on that. But we are going to increase the air gap to 100, and also now we introduced this one is there's no shield iron, but we are introducing the shield iron to reduce the superconductor usage. But I did not compare with all of these things, because I need to first evaluate all of these parameters for our machine, and then we will compare where our machine lie on this one.
So adding the shielding coil, you guys reduce the efficiency, right?
Yeah, I mean that is not very well. I mean, not significant, but it will reduce the air gap flux density little bit. It will reduce, but it will reduce the weight very much, and also we remove the core loss. That is one of the advantage. So it has positive and negative. Thank you very much.